In this lesson, Module 23.1, we are going to learn about modeling with quadratic functions. And what that really means we're going to learn how to do is to write a quadratic function, or which is an equation, to fit a given set of data. So in order to do that, here in video number 1, we are going to learn how to identify a function type from a table of data. Once we know how to do that, we'll learn how to use quadratic regression in video 2 to actually write the function for the data. So let's get started. So one of my favorite sayings goes like this: science explains the universe and math is the language we do it in. And it's not so much a saying as it is a paraphrase of something that Galileo said. And what he meant is that math and science go together hand in hand. So pretend for a moment that you are a scientist. Suppose that you recorded temperature each day for a year, or it could be some other sort of data that you collected over time. And if you wanted to model this data with a function, meaning that you wanted to write an equation for it, how would you decide whether to use a linear model, an exponential model, or a quadratic model? And so that is the topic of the first video in our lesson today. In the real world, a function that describes a situation is not given. Instead, it has to be derived from data that has been collected over time. Okay, so to understand how to decide what kind of equation or model you would use as a scientist, you have to understand the mathematics behind it. So we're going to watch a short video that talks about that.
Sally the scientist is tracking turtles that are colonizing the many islands of the Florida Keys. These two islands, Fun Island and Great Island, Sally calls them F and G for short, have no turtles. One year, let's call it turtle year 0, 3 turtles manage to swim to each of the 2 islands. She returns in 1 year to see how the populations have grown. Wow, the turtles on F have increased to 5, and the turtles on G have increased to 6. A year later, and the turtles on F have increased to 7, while the turtles on G, wow, have increased to 12. She keeps checking year after year, and this is the data she collects. Can Sally find some patterns? Let's look at F. The turtles increase at a constant rate. Sometimes we call that a common difference. We started with 3 turtles and added 2 for however many years have passed. So if 10 years pass, we would have 2 turtles times 10 years plus the 3 turtles we started with. That's 23. If X years pass, then we have 2 times X turtles plus the 3 we started with, and wow, that's a linear function, y equals mx plus b. Sally is starting to understand what's happening. If we graph the function for turtles on island F, we get a straight line, of course. Remember, if the values are created by adding or subtracting a constant, this is a linear model. Cool, well what about the turtles on island G? Here the turtles appear to be doubling every year. So instead of adding a constant amount, we have an annual multiplier, times 2. So for example, to find the turtles for year 7, we multiply 3 turtles we started with times 2 7 times. We can use an exponent to write that. Wow, that sure looks like an exponential function. Y equals a times b to the x. Sally is on it. And here's the graph of the function. Sally's research shows us that every exponential growth function with a multiplier above 1 will eventually exceed a linear function. Eventually there will be more turtles on island G because exponential growth always beats linear growth. Remember, if the values are created by multiplying or dividing by a constant, it's an exponential model. Sam is Sally's colleague, and he's always studying islands in the Keys. He's studying Pretty Island and Quizzical Island. Here's his data for the turtles on island P and Q. What happens to the turtles on island P? The data doesn't look linear, we don't have a common difference. Maybe there's a multiplier at work, which would make this an exponential function. How could we find that? Let's divide each y value by the previous one. If that common ratio holds up, we've found a multiplier. Yup, there it is, 2.5. Here's the equation. And a bigger multiplier means there will eventually be more turtles on P than even G, the other exponential growth island. How about Quizzical Island? Sam missed his data collection on year 0, But on year 1, there were 10 turtles. On year 2, there were 40, and on year 3, there were 90. Those numbers are quite quizzical. There seems to be a relationship to the number of the year. Yes, the y values are just 10 times the square of the year. For 9 years, there would be 10 times 81, or 810 turtles. Quizzical. The function is y equals 10x squared. Do you recognize that as a quadratic function? Y equals ax squared plus bx plus c. B and c are 0, but it's still quadratic. Here's the classic shape of a quadratic, symmetrical. Which turtle population will eventually exceed all the others in the long run? You might think the quadratic, because it grows pretty fast, but nothing can compete with an exponential in the long run. A quadratic has an exponent locked at 2, while with an exponential function, the exponent is x, and x can be as big as we want. We have common difference to detect linear functions and common ratios to detect exponentials, but what about quadratics? One trick is to use the difference of differences. Find the difference from one value to the next, and then find the difference between those differences. If the differences of the differences are constant, then we've got a quadratic. Sam confirmed it. Remember, if the differences of the differences are a constant, you've got a quadratic model. So linear functions have a common difference in consecutive y values. That's the slope. Exponential functions have a common ratio, the multiplier that makes exponentials grow faster than anything else. You can always detect quadratics by finding a constant difference of the differences. Eventually, exponential growth always exceeds quadratic growth, which exceeds linear growth. Thanks for your research, Sally and Sam. So, which island will have the most turtles in the future? The exponential growth function with a multiplier of 2.5 will make Pretty Island a great place for turtle fans to visit. But you really have to like turtles because they will be everywhere.
So here's an example of the kind of problem you're going to see in the first part of your homework. It will say, for the data set below, determine if the function is quadratic by finding the second differences. So in order to carry this out, we have to find the first differences first. So remember, to do that, we take any term and subtract the term before it. So we'll start by doing 7 minus 10. That would be negative 3. We're going to do 4 minus 7, which is also negative 3. 1 minus 4 would be negative 3. Negative 2 minus 1 would be negative 3. And then negative 5 minus 2 is also negative 3. So right now we actually can already answer the question about whether or not this is a quadratic function because our first differences are constant. And whenever our first differences are constant, we know that that's a linear function. However, since the directions said to find the second differences, we'll do that. So second differences, we'll do negative 3 minus negative 3, that will be 0. Negative 3 minus negative 3 again is 0. Negative 3 minus negative 3 is 0. And negative 3 minus negative 3 is also 0. So once again, because those first differences are constant and the second differences are 0, this is not quadratic. So now let's look at another example. Okay, so same directions apply. Identify if it's quadratic by finding the second differences. As with before and with every other time, to find the second differences, you have to begin with the first differences. So again, we take any term and subtract the 1 before it. So 2.5 minus 10 is negative 7.5. 0 minus 2.5 is negative 2.5. 2.5 minus 0 is positive 2.5. 10 minus 2.5 is positive 7.5, and then 22.5 minus 10 is 12.5. So one thing we can tell right now is that this is definitely not linear, so it potentially could be quadratic. Of course, it could also be exponential, but until we find the second differences, we won't know for sure. So let's find those second differences. Negative 2.5 minus 7.5 is positive 5. 2.5 minus negative 2.5 is also positive 5. 7.5 minus 2.5 is positive 5. and 12.5 minus 7.5 is positive 5. So, since our second differences are all constant and equal to 5, we say, yes, this is a quadratic function, and we just list that reason that the second differences are constant as our proof. Okay, let's look at another example. Okay, here's a similar problem where we once again are going to use the second differences to find whether or not this is quadratic. So let's again begin by finding the first differences. So here they are. I went ahead and found them just to kind of save time. And you can see that in this case, the first differences are not constant, so it could potentially be quadratic. So now we'll find those second differences. And so once again, to save time, I went ahead and found those already, and here they are. And we see that they are not constant. Therefore, this is not a quadratic function. So now we might be wondering, what kind of function is this? We know it's not linear, we know it's quadratic. Could it be exponential? So even though your homework will not specifically ask you to figure this out, you may see this another time. So if you remember, exponential functions have a common ratio. So all we have to do is find the common ratio between a term and its previous term and see if those are constant. So let's do that now. So we're going to find the ratio of 180 divided by 120, and that happens to equal 1.5. Let's find the next ratio, 270 divided by 180, and that also equals 1.5. And I'm beginning to see a pattern. If we do 405 divided by the previous term 270, that is also equal to 1.5. And then last, before I run out of room, 607.5 divided by 405 also equals 1.5. And if I had more room, I would continue by taking the 911.25, dividing it by 607.5. But either way, I would find this common ratio all the way across of 1.5. And the other word for this would be common multiplier. And so even though this is not quadratic, we've identified this as an exponential function. And now we have one more example to take a look at. Okay, so once again, if we're going to identify quadratic by the second differences, our first step will be to identify those first differences. So if we do 6 minus 4, we get 2. 6 minus 6 is 0. 4 minus 6 is negative 2. 0 minus 4 is negative 4. And negative 6 minus 0 is negative 6. So we can already establish that these are not constant, therefore this is not linear and could potentially be quadratic. But again, we don't know till we find those second differences. So now let's do that. 0 minus 2 is negative 2. Negative 2 minus 0 is negative 2. Negative 4 minus negative 2 is negative 2. And negative 6 minus negative 4 is also negative 2. So our second differences are constant, which means this confirms we have a quadratic function. And that's all for this video. In the next video, what we'll learn is how to take data once we've identified it as being from a quadratic function and use regression to find what that quadratic function is. So I'll see you in the next video.